Start the recording and share screen. Okay, everyone, can you hear me okay? All right. Welcome to another session of the Weil Conjectures. So today I want to discuss a little bit the historical development of subjects and how people were arrived at this conjecture. So and I want to sort of motivate it from the study of Diophantine equations. So these are equations with integer coefficients. So polynomial equations with integer coefficients. And the goal is to find integer solutions to these equations. So this story apparently started with Diophantus, who wrote a series of books called Arithmetica. So Diophantus lived around 300 AD in Alexandria, and there's a bit of debate as to whether he was Greek or Egyptian or Babylonian. It's not so clear, and there's not so many details of his life also clear. And many of his books were lost. So he wrote apparently a series of books on arithmetic, and many of them were lost, but I think one or two sort of survived through the antiquity, and they were so a particular one of it was translated to Latin in 1621 and found itself on the desk of Pierre Fermat, who so Fermat has an interesting history as well. So Fermat was a lawyer, and he was an equivalent of a Supreme Court justice in France. But sort of, I was reading about his life, and he found like his work so boring, and like people's like usual concerns so pedestrian. So mathematics was for him was a refuge. So he would come home and start writing in his notebooks or reading books about mathematics. It was a way for him to relax. So he was a high official in the whoever the French court was back then in the Justice Department, but he sort of didn't really enjoy it. It was just something that he did, and what he really enjoyed was math, which he would do when he got home. So and of course, it's on the margins of Arithmetica that Fermat wrote his famous last theorem that x to the n plus y to the n equals z to the n has no non-trivial solutions. So here's, by the way, in Wikipedia, here's an assessment of Fermat's work by Andre Weil. So Andre Weil says, what we possess of his methods for dealing with curves of genus 1 is remarkably coherent. It is still the foundation for modern theory of such curves, and naturally falls into two methods. One is called ascent and the other one descent. So indeed, Fermat's descent is still something that's sort of in currency, of course, in modern formulation. And Weil continues, the novelty consisted in vastly extended use, which Fermat made of it, giving him at least a partial equivalent of what we would obtain by the systematic use of the group theoretical method of the rational points on a standard cubic. So we have indeed come across these methods when when Angus was discussing rational points on elliptic curves and how they form a group, etc. So Fermat sort of anticipated many of these developments and used it in his analysis of, in particular, Diophantine equation, but also in sort of pioneering the modern analytic geometry and number theory. So I tried to actually look for the page that Fermat wrote his famed side note, but apparently that was lost. So Fermat's actual book was lost, but his son republished Arithmetica and decided that in this published version, he's going to put his father's comments. I have no idea how he realized that his father's comments are so important, in particular that one comment. So this is the version of the that book that his son published. So this is the page. And then his son sort of added the observation of Fermat into here. And this is some written in Latin. And of course, they didn't use Fermat didn't use notation like x to the n plus y to the n equals z to the n. So, he's talking about, if you take squares, duos, cubos, and look at the equations and go off to infinity like that, like 2, 3, 4, 5, n, then you get, I didn't try to decode the whole message. Google has Latin translator. So I tried to write this out in Google and ask it to translate, but it's not nearly as good. Somehow it was hard to make sense of what was going on. But if any of you knows Latin, you can try to sort of decode what this was. So somehow Fermat's son had the idea that this is important and needs to be published. I have no idea, it's very unusual to republish a book and then sort of include comments by somebody else. Usually you just publish a carbon copy of the original. In any case, this is sort of a bit of history. So there's a comment in the catch. So Diophantus wrote in Greek, of course, yes, ancient Greek. And then it was translated to Latin in 1621. Although Fermat actually read Greek, he knew 6 languages perfectly well, but he was apparently reading the Latin version. And when you look at actually how they used to translate back then, the Greek would be on the right-hand side and the Latin on the left-hand side. It was actually very sensible. So you could, compare the, and I've seen this actually in many books of those eras that were translated into Latin. They would have the Greek on one side, the ancient Greek, and the Latin on the other. Okay. Yeah, I should mention Alexander, not Alexander, Diophantus, who lived in Alexandria. It was during Roman times, but he wrote in Greek because back then, Greek was the common language. Latin became the common language much later, I think. So by 300 AD, it was still Greek was the dominant language. Okay. So, sorry. Let's do some examples. So, okay. The relevant comment for us is that solving Diophantic equations are extremely hard, as the example x to the n plus y to the n equals z to the n shows. I mean, that's just one example that we happen to actually be able to prove now after many, many, many years of hard effort. By the way, just a side remark that the proof that Weil eventually gave, he proved the Taniyama-Shimura-Weil conjecture. So Weil was also part of that story. And that also has an interesting history. Somehow under Weil, during his lifetime, he went back and forth on whether that conjecture is true or not. Like literally, he would say one day that this should be true. And then 5 years later, he would be like, there's no way this is true. Like he was sort of went crazy over this conjecture. Which bears his name and which Andrew Wiles proved. But it's that's a topic for another lecture series. Okay, so Diophantic equations are hard to solve. So let's, instead of trying to solve them over Z, as a first step, let's try to solve them over finite fields. Z mod P, for instance. So study of such equations goes back to probably Gauss was the first who really realized that finite fields are really important in number theory. I'm sure Euler, etc., played with these ideas as well, but somehow Gauss made it systematic. So for instance, as far as I know, these examples are due to him. He showed that x squared minus y squared equals to 1 has p minus 1 solutions, modulo p. More generally, he showed that ax squared minus by squared equals to 1 has p minus the Legendre symbol ab over p solution modulo p. I recall that this symbol is either plus or minus 1, and is plus 1 if ab is a quadratic residue and minus 1 otherwise. And if I've gotten things right, 2 is a generalization of 1. Because a and b are 1, so and 1 is always a quadratic residue. Okay. And in modern sort of formulation, we say that, the geometric counterpart of the story is that we have this equation ax squared minus by squared minus 1 equals to 0 defines a Riemann surface of genus 0. In other words, over algebraically closed field is just P1 minus bunch of points. Okay. However, we are interested. So you might say that P1 minus a bunch of points should have, let's say P1 minus 5 points should have P minus 5 points. So why are we getting P minus 1 or P plus 1 points? That seems a bit funny. And that's because when you go from algebraic closed field to algebraic not closed field, your rational structure might change. So this might not actually be P1 minus 5 points over FP. It only becomes that over FP bar. So the number of rational points also is affected by, of course, by the rational structure. Okay. So one could guess that this equation, when AB is a quadratic residue, then this equation is probably isomorphic to P1 minus 2 points over FP. But if AB is not the rational point, is not a quadratic residue, then it's not, because it has too many points to be isomorphic to P1 minus some points. Okay, any questions about any of these? Comments? Okay. Let's move on. Right, so here's a picture of Gauss with his equations in arithmetic. Probably one of the most famous books in mathematics, perhaps the modern version of Euclid's Elements, in terms of significance, where he sort of unified many different ideas in number theory. So he went beyond, of course, equations of degree 2. For instance, he also considered the number of solutions of equations of this form, of degree 3. And he also considered equations of degree 4. So he was actually was interested in the equations of arbitrary degree. And what he was seeking was reciprocity laws for these equations. So he was sort of fascinated, of course, by quadratic reciprocity, but then he wanted cubic reciprocity and quartic reciprocity. Now we understand that, the modern formulation of that is the Langlands program, but it's sort of, so Gauss was playing as much as he could with the amount of technology that he had then to develop some sort of reciprocity theorem in higher for higher n. But what I want to talk about today is actually not his book, but what's called the Tagebuch, which, rough translation is like, daily book or diary, So Gauss kept a diary only for roughly 18 years of his life. The first entry in the diary is very interesting. The first entry is his proof that the 17-sided polygon, regular polygon, can be constructed using ruler and compass. An incredible sort of achievement, an open question, an important open question at the time. And so this was the first entry in his diary. But what I want to talk about today is actually the last entry in his diary. which happened on 1814. So, and Gauss's Tagebuch was sort of, sitting, was after he died, was given to his son, and then eventually landed, amongst the possession of his grandson. And eventually, this is, 70 years after Gauss's death, Göttingen University was putting together collected work of Gauss, and they asked Gauss's grandson, could you please, give us this diary? We want to publish it amongst the collected work. And that's when it first became public, and when first people saw that the last entry, and the last entry, it became sort of immediately famous. So what does the last entry look like? So we actually do have Gauss's a photo of Gauss's actual handwriting. So you see, this is a page from the notebook of the master, and the last entry is this entry here. Observe by induction facta gravissimo theoremo, an important theorem. And then what is he talking about? He has an equation XX. They didn't know how to write x squared. That notation wasn't invented. So they would write XX. So XXYY plus XXYY. So he's looking at this curve, x squared plus y squared plus x squared y squared equals 1. He's looking at it in Gaussian, so he's using his Gaussian integers. And what's remarkable for me is sort of, besides what it actually says, that Gauss was looking at the point at infinity already. So I somehow had thought that it was Riemann that brought the point at infinity into mathematics. But somehow Gauss knew about the point at infinity. So he sort of, he has like 4 points at infinity, x minus infinity plus minus I, and x plus minus y infinity. Okay. So let's look at the text and what it's saying. A most important observation, facta gravissima, is made by induction, which connects the theory of biquadratic residue most elegantly with the leminiscent. Does anyone know how to say this word? It's a bit difficult for me to say. So these are some class of functions that are interesting, but okay, functions. Suppose if a plus bi is a prime number, and a minus 1 plus bi is divisible by 2 plus 2i, you see how he was doing divisions in Gaussian integers, right? So then the number of all solutions of the congruence 1 equals x squared plus y squared plus x squared y squared, including the 4 solutions at infinity, equals this quantity, a minus 1 squared plus b squared. Okay, let us rewrite this in modern language. Lemniscatic, is that right? Okay. Lemniscatic. I had actually never heard of this word before preparing for this talk. Had you guys heard of this? Somehow, yeah. I mean, when you write the function, it's in the function, of course, but not the word. I just didn't know this word. Okay. And this class of functions, these are kind of special functions that Gauss was interested in. Okay. Let's the Lemniscatic of Bernoulli is the infinity symbol. Not sure I understand that, Joe. But okay, so what does the statement in modern language? So we can phrase Gauss's entry as follows: let P congruent to 1 modulo 4 be a prime. Then it's known that Gauss proved actually that, maybe it was already proved by Euler, I don't remember, that you can write P as sum of squares. This is we teach in our basic number theory course, this fact. And the A and B's are essentially unique. Yeah, so okay, let's fix them by assuming that B is even, and A minus 1 is congruent to B modulo 4. Okay. And let n be the number of points on this curve. X squared plus y squared plus x squared plus y squared equals 1. And we throw in also the points at infinity. And Gauss states that the number of such points is A minus 1 squared plus B squared. Okay. All right, so what does this have to do with the Weil conjectures? So the point is that this curve is secretly essentially an elliptic curve. Okay, it has some singularities, but you resolve the singularities, it's almost an elliptic curve. So let me go to the next page. And so essentially what we're doing is counting points on an elliptic curve. And Gauss is basically giving us an estimate for the number of points. These A and B's, these are okay. So let me go to the next page. So I'm just going to sort of give you a sketch of what's going on. The details. There's a great article by Francis Oort called Gauss's Last Entry, where he goes carefully through all the details of how to connect it with modern number theory and what exactly is going on. But let me just give you a taste. Well, okay, so first of all, this curve that we're looking at is, as I said, is essentially this elliptic curve, y squared equals x cubed after some change of variables. And if you want to see the change of variables, you should look at Oort's article. You need to resolve a couple of singularities, but okay, that's there's some a bit of dance that you need to do. Okay. And then so Gauss is telling us that this this number of points is a squared plus b squared minus 2a plus 1. So therefore, if you look at the a squared plus b squared is p. So if you look at n minus 1 minus p, that's going to be the absolute value of 2a, which is less than or equal to the absolute value of 2 square root of p. So, I mean, he's giving us a bit more information than just this, that is less than or equal to the square root of p. But this fact that, if you have an elliptic curve and you look, so that the number of points on an elliptic curve minus the order of the field minus 1 is always less than or equal to 2 square root of the order of the field. This is the Riemann hypothesis for that elliptic curve. Okay, so in general, Riemann hypothesis for curves is actually equivalent to the statement that the number of points on that curve minus the number of elements in your field minus 1 is less than or equal to 2g times square root of the order of the field, where g is the genus. So in this case, the genus is 1. So this is, and this a plus bi and a minus bi, these are exactly the roots of the polynomial that appears in the rational expression of the zeta function. So in other words, these are the eigenvalues of Frobenius on the étale cohomology, if you know what that is. So okay, so for more details, I refer you to Oort's article where all of this is sort of nicely laid out. Okay, any questions or comments? Okay, let's move on. Okay. So recall, okay, the zeta function of a number field, recall that we mentioned that the zeta function of a number field in general and the function field was defined by Dedekind around. So I'm now going to give you a bit of history of sort of what happened after Gauss and Riemann. So we mentioned that Dedekind defined the zeta function of number field and function field. I looked up Dedekind's life, and the most interesting thing for me personally was that he was born in a city called Braunschweig. The English translation is Brunswick. which is some random city sort of in middle of Germany, okay, sort of exactly close to the border between East and West. And Gauss somehow was also born there. I don't know why it produced such great mathematicians, this tiny city to which I have been. The first time I ever went to Germany to visit a friend, he just happened to live in Braunschweig because there was an Intel office there. Intel is the chip making company, and they had an office in Braunschweig, and they had sent him there for an internship. So I went and visited him. And so an interesting side note is that I got into Frankfurt Airport around 10 o'clock, so made it to the train station around 11. And then I said, well, you know, I want a ticket for Braunschweig. And like, first of all, the lady was confused why anyone wants to go to Braunschweig. So I had to repeat several times that that's indeed where I want to go. And then she's like, well, you know, there's no train going to Braunschweig now. Come back at 5 a.m. And then I was like, well, what am I going to do till then? So at that time, I was still a sort of a student, and, you know, staying in a hotel wasn't really an option. So I was like, well, where can I go that's actually open? She's like, well, the only place that's open is the red light district. So so I ended up spending 5 hours in the red light district before actually making it to Braunschweig. But unfortunately, I didn't know at the time that Gauss and Dedekind were from there. Otherwise, I would have visited their memorials. I'm sure they have some memorials for them. Okay, let's move on. So we mentioned how Emil Artin worked on sort of these zeta functions of elliptic curves, and how he computed sort of 40 different examples, which is quite amazing. Remember, Angus computed one example with the help of computer. And somehow Artin computed 40 different examples, and what came to the conclusion that an inequality such as this should hold. This says FQ, it should be FP. There's a is there a historical record of how much time Gauss spent in the red light district? Yeah, I don't know. Interesting historical question. I don't think he's known as a sort of a playboy mathematician. It's okay. He was known as a tough mathematician. So, for instance, he forbid all of his kids to go into mathematics because he believed that none of them would be as great as him, and therefore they will soil the name of Gauss. So he forbid them. I think one of them did anyway. But yeah, he was not a easygoing man. All right. So this is the inequality that Artin came to conclusion that something like this should hold for all elliptic curves, but he couldn't prove it in general. He just computed many, many examples, and he sort of reached this conclusion. And he also he also, I think, probably he was him who conjectured that the, or maybe it was a bit earlier, that people realized that the zeta function should be a rational function and should satisfy a functional equation. These things also became clear when Artin was computing them, but maybe it was already, people already knew about this. So Friedrich Carl Schmidt was the first person. So Schmidt realized that actually you could prove the rationality and functional equation if you could prove a version of Riemann-Roch for algebraic curves over a finite field. So of course, Riemann-Roch goes back to the work of Riemann and his student Roch. And it has to do, well, there's various ways of formulating it. If you wish, it's like dimensions of the space of meromorphic functions, where you sort of specify the singularity type that you want. Another definition is sort of dimension of sections of certain line bundles on Riemann surfaces. It's one of those theorems that I have actually never quite understood. much to my own shame. It's somehow not a trivial theorem, even after all these years, and it has very far-reaching consequences in the theory of Riemann surfaces. But Schmidt also realized that if you could prove a version of this, I mean, when you look at the statement makes sense actually for curves as well. It's computing some meromorphic functions, space of meromorphic functions. You can make sense of this for curves. So it was a matter of developing the framework so that the statement makes sense and could prove it. So that's what Schmidt did, and then used it to prove Riemann-Roch formula. Used it to prove the rationality of the zeta function and its functional equation. And all the examples pointed to the fact that the roots of these polynomials that are appearing, so this PT, so they knew what polynomial is. On the top, there's a polynomial, I guess of degree G or 2G. So, and all of the roots of it, they conjecture the absolute value is going to be less than or equal to root Q. So the absolute value of the roots has, that sort of, this is equivalent to the statement I made before that the number of points of X minus Q minus 1 is less than or equal to 2G root Q. But nobody knew how to prove this statement. But Schmidt himself proved this statement for elliptic curves. We mentioned this during Angus's talk. Of course, the proof that Angus provided was a modern proof using Tate modules, which sort of came to being in the 60s. But somehow Schmidt in the 1930 gave a proof already of this statement for elliptic curves. But the case of other curves remained open. And there was a whole industry of people who were working on these, like really great mathematicians. But the person who cracked it was Andre Weil. So, and Weil realized that to prove the P analog of Riemann hypothesis, he needed to develop algebraic geometry in not just for curves, but for higher dimensions. And because he realized that there's two different ways that he could prove it. One is to use what's called the Jacobian variety of a curve. So Jacobian variety is the space of all line bundles. That's one definition, line bundles on the curve. And I think people understood how to work with it over complex numbers. Well, maybe even Jacobi did, but not over finite fields. Okay. So there's Weil developed the theory and used it to prove the Riemann hypothesis for curves. That was his first proof. And a few years later, he used intersection theory on X times X, again, a surface, to he developed intersection theory on higher dimensional algebraic varieties over finite fields to give another proof of the Riemann hypothesis for curves over finite fields. And interestingly, maybe 20 years after, so in 1970s, Stepanov and Bombieri discovered the proof, a very clever proof of the Riemann hypothesis for curves, which uses only the Riemann-Roch. So Bombieri was a Fields Medal winner, and Stepanov first, discovered it for hyperelliptic curves, and then Bombieri generalized it to all curves. So in fact, all one needed was, for curves at least, was the Riemann-Roch, although the arguments get quite clever if one wants to just use that. Okay. Any questions about this? There's a comment on the chat. Right. Bios of famous mathematicians, including Emil Artin. Yes. Thank you, Brad. Yes. What is a hyperelliptic curve? That is a good question. I thought the definition was y squared equals, first definition, y squared equals some polynomials in X. If that polynomial was a cubic, then we would call it an elliptic curve. Okay, and if it's higher than a cubic, then we call it hyperelliptic curve. Now, this definition may be a bit of lie, but I think it's maybe suffices to give some idea of what's going on. Is that fair, Angus?
Sorry. Yes. Yeah, that's about right. You just have to note that when you want to consider it as a projective variety, that sort of affine equation, you can't easily embed that into P2. People resolve this in different ways. Some people, I think...
when you say we cannot embed into P2, you mean smoothly?
Smoothly, yes.
I mean, of course, we can embed it into P2 because it's already in A2.
Yes, yes, absolutely. I'm trying to remember I'll see if I can find some notes. Michael Stoll has notes on hyperelliptic curves where he uses weighted projective space, and then that equation works perfectly. You just have to give the variables some weights to make it work, but it's fine.
Okay.
But I would say, but basically, the point is like, I think of the same thing. If someone says hyperelliptic curve, I think y squared equals a polynomial in x of higher degree than 3.
Yeah. Okay. Other questions, comments? Okay. So, all right. So after proving this, then Weil started looking at, it was very natural for him. Now he has a theory of varieties over, finite fields. Let's see if one can count points on these varieties. That's what he's interested in. Of course, not easy thing to do. So I recall the definition of the zeta function works in general, and we gave this definition before, is the generating function for the number of points of X over finite fields as you move over different powers of Q. And it has also a product expansion, and then you replace T by Q to the minus S. That's you get this zeta X of T. And so he was interested in sort of getting information about this object for objects or things beyond elliptic, beyond curves. So it was natural for him. So let's do an example, by the way. So the zeta function of P to the n, projective n space, is 1 over 1 minus T, 1 minus QT, ... 1 minus Q to the nt. And how does that work? Well, first observation is that if you're, if you can, I forget the technical name for this. I think it's excising. But anyway, if you can divide your space into two spaces, U and Z, then they, the number of points of X is the number of points of U plus the number of points of Z. But then remember that the zeta function is actually the exponential generating series. So the zeta functions multiply. So if we write Pn as an disjoint union the boundary at infinity, which is Pn minus 1, then we see that the zeta function of Pn is the zeta function of An, which we already computed to be 1 over 1 minus Q to the nt, times the zeta function of P to the n minus 1. So by induction, we get the expression for the zeta function of Pn that we wanted. Does that make sense? Oops, sorry.
Also a fun question to think about: if I have a product of two spaces, what happens to their zeta functions? That's less obvious.
Yes. Other questions or comments? Okay, so in this P to the n example, we don't get an interesting polynomial on the top. So in general, the polynomial on the bottom, I guess, is going to look like this, but the polynomial on the top is where all the action is somehow. And we don't see it in P to the n. So they had to do some other examples. So let's see what he considered. So the natural thing to consider is hypersurfaces in P to the n. And he considered what we call now Fermat hypersurfaces, because this is a, say, hypersurface, and let's take, I don't know if technically for Fermat, if N0 has to be equal to N1 equal to NR, etc. But anyway, these are the kind of equations that he considered. So just one polynomial equation and no cross terms, you see? So there's no like x0, x1 term. It's just one x0 to the n1 and then x1 to the n1 and so on. There's no cross terms, okay? And he managed to compute the number of points on these, well, more precisely to estimate carefully the number of points on these using results of Davenport and Hasse about Gauss sum, and was able to use this to sort of prove the Riemann package about this variety. So namely, he was able to prove that the zeta function is rational and has functional equation. And furthermore, the most important part, the Riemann hypothesis, that the polynomials that appear in the numerator, the roots have the right sort of absolute value estimates. Okay. So let's actually have a look at Andre Weil's famous paper that started this whole business. Okay. So here's Andre Weil's paper, and it's kind of fun to read through it. So the equations to be considered are of this type. These are the Fermat hypersurfaces, and such equations have interesting history. In his book, Gauss, determines the number of solutions to polynomial equations. So remember, I talked to you about how Gauss discussed polynomial equations of the form ax cubed minus by cubed equals 1, and later ax to the 4 minus by to the 4 equals 1. And then Weil talks about the Tagebuch and the last entry of the Tagebuch, how Gauss proves or at least states a theorem whose truth, it implies the truth of what has lately become known as the Riemann hypothesis for the function field, defined by that equation over field of P elements. So Andre Weil traces his work on these counting number of solutions to polynomial equations over finite field to these works of Gauss. So this was my motivation. Essentially, in the first half of the talk, I was explaining this first paragraph of Andre Weil's paper. Okay, then Andre Weil mentioned some other people that worked on this. So Jacobi, Lebesgue even sort of wrote some papers on this, but he points out that they didn't really get, anywhere with it. So let me see if I can. Without succeeding in bringing out any striking result. This is about Jacobi and Lebesgue. And the whole problem seems to have then been forgotten until Hardy and Littlefoot started working on the problem, and Davenport and Hasse. Okay, and his note is sort of the tone of the note is very interesting. This note will contain nothing new, except perhaps in the mode of presentation of the final result, which leads to the statement of some conjectures concerning the number of solutions of equations over finite fields and their relations to topological properties of varieties defined by those equations over complex numbers. So it was a very sort of modest tone that Andre Weil took in this paper, which in retrospect is played a huge role in 20th century mathematics. Okay. Let's go later in the paper. Let me see. I probably have right. So here we come to the towards the last page of the paper. So he goes through the paper, discusses the example of the Fermat hypersurface, and then says this and other examples, which we cannot discuss here, seem to lend some support to the following conjectural statement, which are known to be true for curves, but which I have not so far been able to prove for varieties of higher dimension. So let V be a variety without singular points of dimension n, and define its zeta function like this. Then the zeta function should be a rational function satisfying this functional equation. And furthermore, the zeta function should have in the rational expression for the zeta function, the roots of the polynomials that appear have to have the correct absolute value q to the power h/2, where h is like, you divide the polynomial into polynomials to p1, p3, p to the n, 2n minus 1. And the reason for this labeling is that these, the degrees of these polynomials, he says, should be the Betti numbers of the variety. And this chi should be the usual Euler characteristic of the variety. So the evidence at hand seems to suggest that if you have a non-singular variety, then the Betti numbers obtained by reduction modulo prime, but by going to complex numbers should be, the same as what we get, the degrees of these polynomials here. So in other words, he's saying that Betti numbers are algebraic, conjecturally, which was a huge surprise for people who were sort of working in topology of manifolds. That Betti numbers of algebraic varieties, Betti numbers of things that are given by polynomial equations have to be algebraic. That's because they can be computed purely algebraically using this procedure. Any question about that? Right. So then he goes on to say that he does one example. For instance, consider, regards to these Betti numbers, consider the Grassmannian variety, the points of which are the R-dimensional linear varieties in projective M-dimensional space. Okay. And what he shows is that he says counting points on these varieties is easy. And when you count points, you discover what the degrees of these polynomials should be. And then he says that Ehresmann, am I saying his name wrong? Ehresmann or Ehresmann, from the world of connections, differential geometry, he computed the Betti numbers of the Grassmannian variety via geometric methods, via methods of geometry or topology, nothing to do with finite fields. And then he says that if you compute the two ways, the numbers agree. So he gives a further evidence why these numbers should be the Betti numbers of the corresponding variety. Okay. Any questions about? So this is where all the magic happens on this page in Andre Wei's, I think it was like a 15-page paper in the Bulletin of the American Math Society, I think 1949. Okay, so there is one fact that Andre Weil knew, which he didn't mention. Namely, he knew that if one could find a cohomology theory for varieties over finite fields, which behave like usual Betti or de Rham cohomology for objects over complex numbers, satisfying the usual properties, Kunev formula, Lefschetz fixed point theorem, that kind of thing, then he knew that the rationality and the functional equation would follow from that. Okay, actually, the functional equation is, now we understand it, and actually Weil already did, that if such a cohomology theory exists, the functional equation is a statement about Poincaré duality. Okay, so but he didn't write anything about this in his note. Maybe it was too speculative. But as I mentioned in one of the previous talks, it was actually this observation or this understanding that sort of galvanized people like topologists like Serre to sort of start thinking about this problem. And eventually Serre brought Grothendieck along, and sort of the rest is history, so to speak. Okay, so this is actually all I wanted to say today. Now I think we're going to have probably one more talk in this lecture series. And the reason is that sort of I'm personally losing, becoming a bit fatigued. You know, all the usual duties of the semester are sort of adding up, and Angus is also quite busy. But we will have one more talk for you about Weil cohomology. So, what sort of cohomology theory are we seeking? What sort of cohomology theory with what properties should a cohomology theory have to explain the functional equation and the rationality of the zeta function of varieties of a function field? So it's a bit of an axiomatic talk. If a cohomology theory exists that satisfies these bunch of properties, then you automatically get functional equation and rationality. But we won't actually dive into how to construct such a cohomology theory, because the construction is quite involved, and I'm not sure if I, have the patience to try to go through it and make it accessible right at this moment. But at least we'll give you a flavor of what. Once we give that talk, then you will know exactly what the field looked like in the sort of 1950s, when Serre and Grothendieck sort of got on the bandwagon. Okay.
I will say, like, it's not just a matter of, to give Masoud some credit, it's not just, oh, I'm too tired to tell you how this cohomology theory is constructed. It is very involved, and I don't think it would be a reasonable thing to attempt in, a few lectures. It's a long course of study to build étale cohomology. Yes,
I think it could be done a bit more humanely, but if one is not interested in the details, right? But yeah, it would take quite time to make the standard treatment into something accessible. It's a non-trivial exercise. Okay, that's it for me. Happy to entertain questions or comments.
Say thank you, Masoud. This was very, very nice. Yeah, we really enjoyed it here. Thank you so
You're
much.
welcome. You're welcome. We'll be in touch. Angus and I will be in touch. Next talk, we're not sure if it's going to be next week or in 2 weeks' time.
Yeah, we'll work that out.
But we'll be in touch about the final talk.
I am also open if anyone has like a personal interest, if anyone has a topic within this area that you would like to hear a bit more about, do let us know, and we might either have a talk about it, or we can like just have a conversation on the Slack or something. So do reach out if you have anything that you'd like to know about, that are questions or ideas that have come up from the seminar or otherwise.
All right. Thanks, guys. Have a nice rest of the day.